Thank you for the introduction. Hello everyone, I am Sadullah, a recent PhD graduate from Boston University. Today I'll be presenting our work titled ProcessorFuzz. This work is a collaboration between Boston University and University of Washington, and I would like to thank our funding resources, DARPA and NSF. So today processors are integral parts of our lives, and if you miss bugs in processors, in the past we've seen that it led to severe security consequences. It has been shown that attackers can exploit these bugs to gain unauthorized accesses by exploiting the virtualization features, or it has been shown that even the side channels can be used to leak many sensitive information, and even the security features like AMD SCV or the Intel SGX, which need to protect our data, were exploited, and then many information could be easily stolen from the servers. And we actually put a lot of effort into verification, yet these incidents happen. Why is that? So one of the reasons is that the processor complexity keeps increasing, and new features in pretty much every generation are coming to enhance security as well as performance. And when these new features come, we need to make sure that they are working as intended, and also we need to make sure that they don't break the functionality of the other features, and they don't introduce new bugs in these features. And there's so many techniques to discover hardware bugs, but we can mainly group them under two categories. The first one is the formal methods, where the goal is to mathematically prove that hardware conforms to the specification, and these methods can be complete and discover really buried bugs, but they have well-known state explosion problem. Another method group is the dynamic verification methods, where the goal is to drive the design under the test with concrete inputs to find the bugs, and these methods are almost always incomplete due to the large input space, but scale quite well. One recent trend in hardware verification is to adapt fuzzing from software domain to hardware domain. And why we are really interested in fuzzing hardware? Because in software domain, we've seen that fuzzing found thousands of bugs in the last years, in the last decade, and they were really serious bugs that led to severe consequences like leaking information or gaining unauthorized accesses in the servers. And our work, ProcessorFuzz, is another hardware fuzzer, simulator-based hardware fuzzer based on a new hardware-centric coverage metric. And it is scalable to complex processors, as we have seen in our experiments, and it is really easy to integrate into different processors. Before going into the details of our work, first I would like to give a background on software fuzzing and also related work. Software fuzzing is basically an automated testing technique, and the goal is to generate a large number of inputs and execute the program under test with these inputs repeatedly to trigger bugs. But this definition sounded like we are like a monkey, like we are blindly testing programs without understanding it. And actually, it's correct. This simple form of fuzzing is called as black box fuzzing. But later researchers show that we can do better than black box. And rather than generating inputs from scratch every single time, we can collect feedback from the program under the test and drive the input test generation with this collected feedback, and actually generate inputs with feedback-driven. We can mutate the inputs with feedback-driven information. And most of the time, this feedback is the coverage feedback, while there are other feedback mechanisms as well. But one of the main widely used feedback mechanism is the coverage-based mechanism. And obviously, there are fundamental differences between software and hardware, and we cannot just take the software fuzzing and use it in hardware domain. The type of inputs that we need to provide to software and hardware is different, and also how we execute the hardware versus software with these inputs differ. what kind of feedback we can collect from software and hardware differ, and finally, how we identify bugs in software and hardware differ. And the focus of our work is the feedback type mainly, so I won't go into the details of the other aspects, but mainly we'll be focusing on the feedback type here. And I would like to talk about two important prior works and how we are mitigating the shortcomings of these works. So, and I would like to use one small logic here to explain the shortcoming. RFuzz is relying on multiplexer selection signal toggle coverage, where the intuition is that if we can drive the fuzzer in a way that it is generating test inputs to toggle different multiplexer selection signals, we can essentially cover different hardware regions. And the problem with this approach, as shown by diffuse RTL, is that it is not scalable because there are so many multiplexers that we need to monitor, and therefore diffuse RTL propose a scalable approach, namely register coverage. They don't track every single register, but rather than that, they track any register that indirectly or directly affect the value of the multiplexer selection signals. So the goal here is that since the number of registers that track of this multiplexer selection signals is significantly lower, it is becoming scalable and the instrumentation overhead becomes significantly less compared to our fuzz approach. But we observed that while detecting these registers, diffuse RTL monitors many data path registers that mislead the fuzzer. With a more specific example from this logic, this is actually taken from Rocket Core, and we observe that the value of remainder register can easily change. So if your test input includes a multiplication operation where you multiply two numbers, let's say, you can see coverage increase in your processor. But the question is it really so interesting to generate more inputs with an input that includes just a couple of multiplication operation? And as you can see in the figure on the y-axis, we present the register coverage, and on the bottom you see over time how much multiplication and division component contributes to the coverage. It is like the huge part. And in our work, ProcessorFuzz, we rely on control and status registers that form the core of the ISAs. And specifically, our intuition is that certain CSRs dictated by ISA already expose the current FSM processor state. And if we monitor the transition here, we can actually test different and interesting hardware events, such as the current privilege mode can change or an event that causes floating point mode exception. And by monitoring these transitions in CSR, we actually know what kind of CSRs we monitor and eliminate the issue of this misleading coverage coming from the data path registers. Another important aspect of our work is that it relies on ISA simulator as part of the coverage feedback mechanism, and this has two advantages. The first one is we are able to understand interesting input faster because ISA simulator is roughly 100x faster than RTL simulator based on our experiments from Rocket RISC-V processor. And that's why we can identify bugs faster. And also ISA simulation-based feedback requires almost actually no HDL-specific RTL instrumentation. So we can just instrument the ISA simulator and adapt this to different processors that rely on the same ISA. Here is the design overview. As you can see, we start with seed corpus that includes a set of inputs, and then schedule one of the seeds from here, generate new inputs, and then provide these inputs to the ISA simulator and obtain ISA trace log, and monitor the CSR transition in this ISA trace. And if you observe a new CSR transition, we launch the RTL simulation and compare the trace log coming from the RTL simulation and ISH simulation to understand if there's a potential bug here. We evaluated our approach in 3 real-world open-source RISC-V processors. Rocket Core and Boom Core are chisel-based, and Black Parrot Core is system Verilog-based. We use Spike and Ramoja as the ISA simulator, and we compare ProcessorFuzz with no-cow diffuse RTL and reg-cow diffuse RTL, where the first one is pretty much a random instruction generator, and the second one is the actual diffuse RTL with register guidance. And we fuzzed 44 hours and repeated the experiments 10 times since the fuzzing is quite indeterministic. And we tested our approach on known bugs as first, and from Rocket and Boom Core specifically, and observed that compared to no-cow diffuse RTL and the reg-cow diffuse RTL, we achieved 1.21 and 1.23x speed up respectively. And also in the plot, you see how much register coverage each approach achieved. Although over time, ProcessorFuzz achieved the least register coverage, it was still able to find the bugs faster, because just because you have higher coverage doesn't necessarily translate to faster bug discovery if your coverage metric is not well suited to fuzzing. And we also found new bugs in Black Parrot, Ramoja, Rocket, and Boom cores. In total, we identified 8 new bugs in this real-world processors. And you can see more information in the paper about these bugs. We also measured the speed up achieved by processor for these new bugs. And actually, since diffuse RTL doesn't have support for system Verilog and it requires huge effort on our end, we could only compare it with random generator and observe that one bug could be only found by ProcessorFuzz, and on average, we achieve 1.6x speed up. In summary, in this work, we propose a new hardware fuzzer that specifically targets processors, and it is guided by CSR transition coverage feedback. We determine interesting inputs based on ISA simulation, and we expose 8 new bugs in established real-world RISC-V processors. And here are the references that I have, and thank you so much for listening to me. I'm happy to take any questions now.
We have time for several questions. Please.
Hi, it's Ryan Helensky, Sandia National Laboratories. So you're talking about bugs where the simulation model doesn't match the hardware implementation here. Have you thought about how to apply this to what do we call them? Logical side channel bugs like meltdown and Spectre?
So this work particularly doesn't focus on any side channel. It is merely focusing on functional bugs that needs to be specified clearly in a spec. But there are fuzzer works in hardware domain that actually target side channels as well. But the way to go about it is obviously different than what we do here. And yeah, you can refer to those papers how hardware fuzzing can be leveraged in that domain.
Right, so you could define new metrics to try to discover new bugs, new types, with your work, right? Okay.
Thank you for asking.
Any more questions from the audience? No more questions? I can ask a question.
Yeah, sure.
You have done both RTL simulation and ISA simulation, and when you applied the fuzzing, did you apply to both or one?
So there's a coordination here, basically. So first, ISA simulation, right? Our first step is to make sure that there are CSR transitions in ISA simulation. But eventually, since we also run this, derive this inputs to the RTL simulator as well, eventually we are actually fuzzing both, and we can find bugs in both ISA simulator and RTL simulator. But our definitely final goal is to find the bugs in RTL simulator, but we observe that sometimes ISA simulator is wrong. So there are problems in ISA simulator as well, and actually one of the bugs that we found here, the Dramoja one, for instance, we observed that RTL is correct, but ISA simulator is wrong in the implementation of spec.
Oh, then thank you so much. Let's
Thank you.
Thanks the presenters once more. And yeah, thanks everyone. Yes, the second paper title is Targeted Bitstream Fault Fuzzing, Accelerating BiFi on Large Designs. Okay, and I'll introduce the speaker. Please. Maik Ender, having received both a BS and MS degree in information security from Ruhr University, Bochum, Germany. He's currently pursuing a doctoral degree at the Max Planck Institute for Security and Privacy in Bochum, Germany, and conducting research in the fields of hardware Trojan, FPGA security, and FPGA internals like Bitstream security schemes. Just get to the, this one. And then here, show from, okay. Please. Yeah.
So thank you very much for the introduction. This is joint work with Susanne Engels and Christof Paar, and Susie, she can't sadly be with us today as she is giving birth to her next child in the next few days, so customs wouldn't let us in. So this is your everyday FPGA board, of course, huh? And right there in the middle, there's your FPGA. And FPGAs are fairly cool devices as they can be reprogrammed with any hardware design you can imagine. And under the hood, there is this reprogrammable array of basic elements, so of these lookup tables, flip-flops, and the reprogrammable routing. And these lookup tables here, they tend to be the gates within the design. So you can program them with any Boolean function you want. And programming the FPGA and all these functions into it is done by loading the so-called bitstream. And you can load then your design, so all your CPUs, IP cores, anything you want, and of course your cryptographic cipher. So for example, your IAS design. And as we are here in the security domain, you can attack FPGA designs as any hardware design as you want. And for example, we take out our everyday laser and shooting onto this FPGA, you're carrying out some fault attacks. And with these fault attacks, you change the inner status and corrupting this inner status of your cipher. And so with some magic, we will later see how you can leak out this, the cryptographic key out of your design. But besides these laser fault injections and other fault injection methods, we have another attack surface here on FPGAs, namely the bitstream. And by manipulating here this lookup table configuration, we're manipulating the Boolean function of a gate. So again, we just manipulate the Boolean function of this gate by just manipulating the LUTs configuration. And so to speak, we introduce static faults into FPGA designs. But what is the problem with these kinds of attack? Nowadays, we have FPGAs which are fairly large. And we don't know which of these gates, which of these lookup tables we have to attack. So we have to test every lookup table within the design in this kind of brute force manner. And nowadays, FPGAs become bigger and bigger. So here in this Xilinx 7 series devices, we already have 1.2 million lookup tables per design. And even in the next series, in the UltraScale series, for example, there are more and more upcoming lookup tables. So, and within our tests, we see that we need roughly 400 seconds per lookup table to test, so loading the bitstream, querying the cipher, and so on. And these 500 seconds times 1.2 million results in a worst-case attack time of 182 months, so not rather practical. So in our work, we try to target the bitstream. We try to target the specific lookup table which is vulnerable to to an attack. And we do this by finding the LUTs automatically by reverse engineering. So we can reduce the attack time from hours or years to just minutes or hours. So what can go wrong on these AES designs? So here we have our AES cipher, and in the top you see there's the plain text, the ciphertext coming out at the bottom, and it's calculated in these 10th round of permutation and substitution layer. And playing around with that, a lot of things can go wrong. So example, setting the S box to 0 will kill all this non-linearity layer, for example. And what we will do later is to try to find this round counter, so the done signal of the AES design, so to skipping all the different rounds which are calculated, so that only one round is calculated, and we then easily can invert the cipher. So how have we done this? Well, let's give a brief outline of the attack and then see how every step is conducted. Right? So first, we have to take out the bitstream and convert this proprietary format to a human-readable format. Then we have to identify the vulnerable LUTs within the bitstream, so we know which lookup tables we have to attack. And here maybe we get a set of different lookup tables. Then we have to manipulate the bitstream accordingly, and then, of course, carrying out the fault injection attack. And here in the second step, there is our main contribution. So we build up this work on the bitstream fault injection attack work of Swisinski et al. And mostly does this on this second step here. As a small side contribution, we also applied this to the Xilinx 7 series devices, as the original attack was done on the 6 and 5 series devices. Okay, so first we have our bitstream, which can be copied from this non-volatile memory, and then using the bitstream database from the open source project, Project X-Ray, which they have generated a database of this bitstream format. And they introduced this FASM format here, so this FPGA assembly format. So you have a line with every basic element in the FPGA. And here, for example, in this marked area, you see that this is the lookup tables init string of the DLUT in the slice X12Y112. So you know the Boolean function of this gate. Then we can take this FASM file and convert this also with the Project X-Ray tools to a Verilog netlist, and then progress this further. Okay, so in this second step, we want to try to identify these lookup tables which are vulnerable. And again, we want to try here to find this done signal, so we can skipping all the rounds, just but one round of the AES design. So we take the Verilog netlist from the step before and put this into HEL. HEL is a gate-level netlist analyzer. It's an open source software for analyzing netlists and doing all the reverse engineering work. And also there is this algorithm called Dana. And Dana can group all the flip-flops which are in the design and group them to word-level registers. So this is interesting for us, as AES used to have 128-bit registers, right? So grouping all the flip-flops in this flattened netlist, which we had from the bitstream before, to registers of 128-bit size or 32-bit sizes and so on, so we can reduce the interesting part which we want to see, right? So we get a bunch of registers out. And then we need to identify a single lookup table which we want to attack. So see here, you have this 128-bit registers, a bunch of of flip-flops carrying out together. And then within our experiments, we saw that only the last register in the AES design has this done signal connected to it within the clock enable signal. So we're tracing down from this 128-bit register a clock enabled signal and seeing that this done signal is computed in one single lookup table. And this single lookup table we have to attack. And of course, as this function is done in many lookup tables can be done, we get several lookup tables, right? So we get multiple lookup tables, so we call our attack fuzzing, right? We get some lookup tables. So we identified these lookup tables, and then carrying out the bitstream manipulation by some custom manipulation tool, again built on this FASM format, right? And we manipulating the bitstream only at the exact points where this lookup table is, so no resynthesizing the design or anything else. So we get out a bunch of bitstreams, and these bitstreams we have generated, we can load them to the FPGA, querying the cipher, so we get hopefully faulty ciphertext out, and hopefully one of these ciphertext leaking then the key. So of course we did several case studies, and as I mentioned earlier, we tried first the bitstream fault injection on the 7 series devices. So we took out the 11 AES designs which were open sourced from the original BiFI paper and tried them on the 7 series. And interestingly, 2 out of these 11 designs didn't work on the 7 series because now it's on the new series with the evolving synthesizer, so Vivado and not the old ISE tool flow anymore. So the synthesizer packed the lookup tables a bit more, so there is not the single lookup table which can be attacked easily. Of course, then we take out the 9 working AES designs and attack them with our targeted bitstream fault fuzzing. And here you can see the designs, so the various AES designs range from 550 to 1,600 lookup tables. And there we found in the designs only 1 to 3 target lookup tables. So we reduce here the number of points where we need to attack from these 1,600 lookup tables or gates to only 1 to 3 target loads. And this directly corresponds to the runtime of the attack. Right? So with our TBFF attack, we only need 6 to 20 minutes to attack the AES design and get a key out of it. And comparing this to the brute forcing BiFI attack, which needs 60 to 180 hours, we have the speed of up to 1,600. And here's a small side note. Again, 2 designs didn't work well. Again, as our algorithms didn't find this single lookup table to attack. But of course, this is interesting for future work to see if there are different methods to find these vulnerable lots. As well, we tried to combine these with some other designs, combined a reference design D3 with some other cores. And again, here we only find 1 to 2 target lookup tables in the design and got here again a good speed up as TBFF runs only 10 to 15 minutes while the BiFI attack would take up to 1,300 hours. So again, a speed up of over 6,000 here. Okay, so coming to a conclusion and wrapping this again up, we had these 4 steps we have to carry out to carry out this attack. And quickly thinking about countermeasures, we can counter, of course, with bitstream protection mechanisms, so encrypting the bitstream or authenticating this. But on Xilinx 7 series devices, this is already broken, and on ultra-scale devices partially. So we can maybe counter the second step with some netless obfuscation schemes. But of course, then maybe we can again come up with some other mechanisms to counter these obfuscation schemes as well. But of course, fault injection countermeasures can help here as well, so duplication or these other countermeasures. So to conclude, we find these vulnerable LUTs completely automatically, so no manual reverse engineering anymore. We can drastically reduce this number of bitstream manipulations by that, so only finding 1 to 3 target LUTs. And so we can enable bitstream fault attacks on large-scale designs again, and having this attack in a practical way again. So thank you very much, and any questions?
We have time for maybe 1 or 2 questions. No questions from the audience? Okay, please.
Thank you for this talk. Just a question. You propose to use Bitstream encryption and the countermeasure. Do you think that is also interesting to use Bitstream compression that is always proposed for many different FPGA? Because when you have the fault injections, you could impact more bits that you want.
You mean bitstream compression, right?
Yeah.
I don't think so, because we already understand the bitstream compression format of Xilinx. And so, of course, you can come up with other compression mechanisms, but you can decompress it as well on the computer, right? So I would say it's rather an obfuscation mechanism than a security mechanism, right?
Okay.
So maybe it's an obfuscation with some own compression mechanism, but the Xilinx format is already understood.
Okay.
Yeah.
Interesting.
Any other questions from the audience? No more questions? Okay, then let's. Okay, thank you so much.
Thank you.
And thanks so much. First page, I guess. Just go to the screen. And, which one is this full screen? No, it is this one full screen, I guess. Yeah. Here you go. Yeah. Okay. Let me just introduce you. Okay. I did it, but here, I've done it here. I know, but
here it shows the PDF, but not on the.
It's a PDF. Yeah, that's. Should I switch the screen or?
PDF one, you can use the Adobe Reader.
Close this one. Closing the others, maybe.
Just go to full screen. Yeah, okay. Now,
No, it's not showing. We need to close all of this. Yes. Yeah, sorry about the technical difficulty. It's resolved, and the last talk in this session is about EC-CFI, control flow integrity via code encryption, counteracting fault attacks. The presenter is Pascal Nasahl. Hopefully I have pronounced his name correctly. He's a PhD candidate from Graz University of Technology. In his research, he focuses on mitigating different threats using cryptographic computing. Please welcome.
Thank you. Thanks for the introduction and thanks for joining my talk here. So my name is Pascal from TU Graz. And this is a joint work together with colleagues from Intel Labs. And in this paper, I want to show you how we mitigate control flow attacks, fault-induced control flow attacks using cryptography, namely the Intel TME M-key memory encryption engine. For this threat model, we are considering an adversary that is capable of injecting one or multiple faults into the processor. We model the effects of these faults as either bit flips or stuck at 0 or stuck at 1 effects. And these attacks were pure local attacks a couple of years ago. So we had to go to the chip, we had to decapsulate it, we had to shoot a laser into the chips. But as we heard this morning, for example, new attack methodologies such as Walsh Jockey or Plunder Vault or Clock Screw also allow us to do these attacks remotely in software, meaning that also the attack surface grows, so we can do these attacks even in the cloud. Therefore, we need new countermeasures. In our work, we especially focus on control flow attacks. So we want to protect the control flow against fault attacks. I've here a small program. This small program consists of 5 functions, ABC, secret, and non-secret function, and I've represented these functions in their call graph. The call graph basically comprises all the valid transfers from one function to another function. So A can call B, B can call the secret function, and so on. And the goal of the adversary is now to induce a fault in such a way that we are basically escaping this call graph. As you see here, we jump from the C to the secret function. This is what we want to protect, and this is what this paper is about. How can we do these attacks is also a very interesting question. So I have here a call instruction, a code snippet that calls basically the address which is stored in the RIX register, and we can manipulate the control flow by, for example, manipulating the instruction encoding. So we can here change this RIX to RCX, for example. We can flip bits directly into the register, so we therefore can manipulate the control flow. We also can manipulate the CPU pipeline, so just think of the address generation unit in a CPU. If we induce faults there, we also can hijack the control flow. Last but not least, instruction pointer is also quite a famous target to basically hijack the control flow. And we want to mitigate this threat by introducing cryptographic control flow integrity. The basic concept is really simple. So what we do is, before we're starting the program, we're encrypting each function using a dedicated encryption key. For example, A is encrypted with this brown key, B with this blue key, and so on. During runtime, we are now dynamically deriving the decryption key, and before we actually switch this function, so for example from A to C, we need to make sure that this key is in place and that we can fetch the code here. Advantage here is if we have a control flow hijack, as we have seen here in this example from C to the secret function, we have a key mismatch, and with a very high probability and with a minimal detection latency, or even no detection latency, and we can detect that there is something that's going on wrong. Another question is, how can we actually implement this on recent Intel CPUs without any hardware changes? So we don't want to make any hardware changes. We want to use the hardware we have here. We had a look into recent features of modern Intel CPUs. This is the Intel TME M-key engine. So TME stands for total memory encryption, and M-key for the multi-key feature. So we can have multiple keys to do memory encryption. And you find this Intel TME M-key engine, for example, in Raptor Lake, Sapphire Rapids, and so on. So the basic idea of this scheme is that we have a memory encryption engine which is placed between the core and the memory controller in the memory bus, basically, or in the memory interface here. And internally, this memory encryption engine consists of a table. This table comprises a mapping from key ID to a key. So key ID 1, for example, is mapped to the key BBB. Now, how does the TME M-key engine knows which key to use? Well, basically, this key ID, this red one you see here on the slide, is embedded into the upper bits of the physical address. So if you have a memory request, these upper bits basically define which key we want to use. Now, the question is, how can we set this key identifier in the physical address? Well, we do this by setting the corresponding page table entry. And this also basically leads to, so how does, basically this gives also the limitation of this scheme. It's basically meant to be page granular. So we have one key per page. And for many, many applications like memory safety, like different stuff, and also our cryptographic control flow integrity, this is too coarse-grained. We want to have a more fine-grained scheme. And this is basically the main contribution of this paper. We show that we can have fine-grained memory encryption on Intel CPUs with this TME M-key engine without any hardware changes. As it's a bit more complicated, I want to start very easy. So all of you, I guess, know how address translation works in modern CPU. So we have the linear addresses, which are also called virtual addresses, and we have the physical addresses, which are basically the addresses we have in DRAM. If you want now to translate the address, for example, of this function B is here on the left side. We do this by using the address translation mechanism of the CPU. The address translation mechanisms of the CPU uses the page tables to basically decide or to resolve this address, and then we're getting the physical address using this page table here. So this is really simple. Now if you use a hypervisor, so if you're using virtualization, with the Intel virtualization feature, we have a second level address translation mechanism. So this basically looks like this. So we have the guest linear addresses and the guest physical addresses, and we're using the page tables as we've seen before in the level 1 translation to just translate our addresses. Then the second level address translation is a bit different. Here we call these page tables extended page tables, and basically it's the same or it's quite similar, and the CPU also uses these extended page tables to do the second level address translation. So if we want now to translate the address of function B from the guest physical address space to the host physical address space, we basically use this extended page table here. And if we now set the key identifier bit in this extended page table entry, as you see here, then during address translation, this key identifier bit automatically gets set in the physical address, which means that the memory encryption engine now encrypts or decrypts the memory object with this key. This is, for example, the blue key here. Problem is, this is still page granular, so this is not what we want to have. Now in our work, what we do is that we establish for each of the key we want to use a separate extended page table. So in this example, we want to have 3 different keys, yellow, blue, and green. So what we do is that we just establish 3 different extended page tables, and they have the same mapping from guest physical address to the host physical address. So the page frame number is the same. However, there's one difference here. We basically swap out the different key ID fields. So key ID 1 for extended page table 0, and so on. Now if we want to access again function B, and extended page table 1 is active, we're using this blue key to encrypt or decrypt data. If we now switch to extended page table 2, we're using the green key, and we now access function C with this green key. So quite simple. Now the question is, how do we do the switch? So how do we switch from extended page table 1 to extended page table 2? Well, we do this by using the VM-func instruction. This is a virtualization technology instruction which is from user space. You can't call from user space, and it allows you to basically switch this extended page tables quite fast. And this function uses the index as a parameter. This index maps to our extended page table pointer, and this extended page table pointer maps an extended page table. So this is how this works. And now by just calling this instruction, we can switch between these extended page tables. If you have now the wrong extended page table active, for example, this extended page table 2 with the green key, we want to access the previously encrypted code, which is, for example, the blue key, we have a decryption error. So we basically just fetch garbled instruction. This is not what we want. All right, now let's put things together. Let's build cryptographic CFI via TME key. What we do is basically at compile time, we assign each of the functions in our program a dedicated extended page table and the extended page table pointer for that. So for example, a function A uses the extended page table 1, which uses key identifier 1, and so on. Now, when we load the code into memory, what we do is that we basically load code block for code block separately, and we switch in between, so between 2 encryption domains, we're just switching this extended page table pointer, meaning that we're also switching the encryption key. And when we're done with loading the program code, we basically have ensured that each code block is encrypted with a different key. At runtime, what we need to do is we just need to make sure that the extended page table we used previously is already active. So if we go from A to C, we need to make sure that the extended page table for the violet key is actually in place. This is more, so how do we do this in more detail? Well, we introduce basically a global register R. This global register R stores the current extended page table pointer. And this extended page table pointer maps to an extended page table. This extended page table consists of a key. What we do then is we basically derive this EPTP dynamically. So we do this by just adding the current register value, which is the extended page table pointer, plus a position-dependent constant. And this addition basically gives us then, if you're doing the right control flow transfer, the correct extended page table pointer, which is in this case the extended page table pointer 4. And before we do actually the call instruction, we need to make sure that we switch to this extended page table using the VM-func instruction. All right, if we have a mismatch, so if we jump from function C to the secret function, but we have still extended page table, this violet extended page table active, and we want to access code with this yellow key, well, we have a mismatch, and this basically means that we fetch garbled instructions. For the implementation, we implemented our proof of concept by using LLVM toolchain. So we developed a modified LLVM toolchain, which does the automatic instrumentation of code. It basically automatically derives this extended page table pointer, and it also initiates the ePTP switch using the VM for construction. We provide a loader, which is basically responsible for taking care of loading code blocks into memory with the different encryption keys. And basically, it also is responsible for setting up these extended page tables we want to have. For the hypervisor, so we need a hypervisor for our thing to work. The hypervisor basically provides the functionality of allowing us to have different extended page tables, and it also supports the switching of these extended page tables. This is basically the implementation here. For security analysis, so if you have a fault in either instruction pointer, return addresses in registers, caches, wherever, or it's in the pipeline, then we basically still are able to manipulate the control flow. We can jump from A to C, for example. But the problem is that now that we have a decryption key mismatch, so we are using a different key to decrypt the code than we use to encrypt the code. Basically, what the instruction fetch interface gives us is some garbled instructions. And in the instruction decoder of the CPU, this garbled instruction yields with a very high probability an illegal instruction. And this means that we can immediately detect a control flow manipulation. Now about the performance overhead. So we compiled binaries with our toolchain. So we had a look into spec and mbench, and we basically executed them on an Intel CPU. Problem is that the overhead is really high. So we have a runtime overhead of factor 6, which is pretty high. For this, we had a closer look in what actually is going on wrong. So what is the problem here? Well, basically what we found out is that we are massively increasing the TLB pressure, or the pressure on the TLB, which basically means that we don't have any TLB, or the positive effect of a TLB is not as visible as it should be. Therefore, we propose a minimal hardware modification of how the TME-MKey engine actually works. So currently, the TME-MKey hardware engine fetches this key identifier from the physical address, and we propose instead, why not introduce a key identifier register, which is really similar to the PKRU register of other Intel features, and basically use the key ID from this register. Then we don't need any APT aliasing anymore, and we emulated this, and we got a reasonable runtime overhead of 1.21, which is, I guess, quite okay for a full countermeasure. For conclusion, I showed you today what cryptographic control flow integrity is. Basically, we ensure that the call graph cannot be escaped, and this gives us no or minimal detection latency. The main contribution of this work is actually the fine-grained memory encryption on Intel CPUs. So we showed that we can use this feature beyond its intended use case. The granularity is basically block cipher, so we can go down to this block cipher granularity. And as I'm a really big fan of using cryptography as a technique to mitigate different threats, I'm really eager to see what others do with this concept here. We also provide an open source toolchain, and we implement a customized loader and hypervisor. And with this, I'm at the end of my talk, and I'm looking forward to your questions. Thanks.
Yes, we have time maybe for 2 or even 3 questions, please.
Hey, yeah, good work. Thank you for the presentation. I have one question related to the way that you exploit this attacks. So basically, can you please clarify why existing control flow integrity hardware features cannot protect against these attacks based on the example maybe that you put there, like for instance, Intel CET, right? What would be the problem here that Intel CET would be missing?
That's an excellent question, thanks. So Intel CET basically only considers a software adversary in its threat model. So this is how it was built. This means that it only protects first and foremost indirect calls. So direct calls are not protected, and we can do these attacks also for direct calls. And we can do these attacks also for instruction pointer, for the HEU, also for the address generation unit, and stuff like that, which is basically not considered by Intel CET. So it's basically, I would say, it's a different threat model, and this is also why we need different techniques. And also, other control flow integrity schemes, so there are software-based control flow integrity schemes available, which also have threats use fault in the threat model. Problem with them is that they have some kind of detection latency. So usually they are signature-based approaches. They basically check constantly whether a signature, the derived signature matches the expected signature, but this also means is because these checks are quite costly, they're only placed at, for example, the end of a function or something like that. That means we have some time to actually still execute some instruction. And with this, we have no detection latency, which is also a pretty neat concept, I guess.
Thank you. Another question that I have. So is this solution, right? First, can we see this kind of issues in other ISAs, right? Processor flavors like the AMD-based processor, RISC-V-based processors. And also, do you think that your solution here is specific to Intel, or you can, AMD has also encryption features, RISC-V has those as well.
Yeah.
Can you come up with, like, obviously not right now the concrete answer, but at least you can. Did you think about this other, ISAs?
Yeah. So the attacks definitely work in all different ASAs. That's definitely the case. We can use AMD's memory encryption engine for the same purpose, I guess. So we already have thought about doing this. So this is definitely possible, I guess. For RISC-V, so there are already tons of cryptographic control flow integrity schemes out there. For example, my colleagues implemented themselves. The main contribution of this work is basically that we don't need any hardware modifications. So it's easy to do a cryptographic control flow integrity scheme when we have hardware modifications available, but it's not that easy if we are limited to what we have. That's basically the key message here.
Okay, thank you so much.
Thank you so much.
Still, we have time for maybe one more question. No questions from the audience? Okay, please.
Thank you. I believe you that there is a high probability of wrong decryption if the key is not the good one. But did you measure the number of cycles before to generate an illegal instruction? And how many cycles?
Yep, that's a very good question. Problem is the x86 instruction set is quite dense. So it could be that we have an instruction which got the wrong key, but it's still a legal instruction. So this is definitely possible. But however, I argument that an attacker wants to execute specific instructions in the code or not some instruction. So this is the first argument for it. And also the likelihood that we detect this problem after 2 or 3 or more instruction actually is quite high. But no, we did not perform an analysis for that because it's also not quite clear how many instructions are there and how are they encoded with the different encodings and stuff like that. So it's really hard to do this, yeah.
Okay.
But we also have thought about this, yeah.
Thank you.
Thank you.
Let me just ask the final question from you. And how do you compare this with like control flow integrity method or mechanism that we have from Intel?
This is basically the CT feature, you mean?
That's called control flow integrity. That's for flow of the instructions. Here, I think what you have is at functional level.
We have this as function level. So
Not
yes.
at, okay, then this is like a complement to that.
Exactly, yeah.
Okay. Thanks so much, and thanks everyone for your time. I hope you guys have learned something from the